previous videos, we looked at how to find the most powerful test of size alpha for a simple versus simple set of hypotheses. So a simple null and a simple alternative. So in this last video, we're going to explore a little bit on how you would generalize that from a simple null and simple alternative to a simple null versus a composite alternative. And really the idea is that if you have a simple null and a composite alternative, the critical region C is a uniformly most powerful critical region of size alpha if C is the best test based on the Neyman-Pearson lemma against every simple hypothesis in the alternative. And the important thing here is that now we're thinking about the uniformly most powerful test, so that means for any value in the alternative. So we'll talk about two strategies here, and I'll briefly mention one, and then we'll spend a little bit more time on the other. So the first strategy for finding uniformly most powerful test would be just to think about your null, simple, and your alternative as composite. So this really says that your value is something in the parameter space that's not under the null hypothesis, so that certainly could be composite if the parameter space is large. And so what you could do is derive the Neyman-Pearson test, which we've had plenty of practice with, under a particular alternative in this set, and then try to show that actually it doesn't really matter which specific value you use, because if you move that specific value around, you would still have the same set of inequalities that you derived. But we should note that that doesn't always happen, so it might be the case that there actually isn't a uniformly most powerful test for a given null and alternative. Now, one way that would happen is if you had data from a normal distribution and you were testing that the mean mu is equal to some value versus not equal to, so a two-sided test. In that case, you won't have a uniformly most powerful test. So things get a bit easier if we have a sample from the exponential family. So just as a reminder, a random sample comes from the one-parameter exponential family if you can take the PDF of the data, so that's the joint PDF, and factor it in a certain way. So you have your A of theta, so A is just a function of the parameter, not of the data. B is a function of the data and not of the parameter. And then you have E raised to C, function of the parameter, and D, function of X. And from our previous study of the one-parameter exponential family, we know that if we can write our distribution like this, then D is a sufficient and complete statistic for the distribution. And so if we have a sample from this distribution, then if our C, the C function, is increasing as a function of theta, then we can get a uniformly most powerful test for two different scenarios. So the first scenario is when you have an upper-tailed test, meaning the alternative hypothesis has a greater than sign in it. And in this case, we would reject the null when our sufficient and complete statistic is greater than or equal to k, where again k is chosen to be a test of size alpha. And in the case where we're testing a lower-tailed test, so the alternative has a less than sign, then we can get a uniformly most powerful test of size alpha if we reject d of x being less than or equal to k. Again, k is chosen to be a test of size alpha. So we'll look at a quick example. Suppose we have an IID sample from a normal distribution where we know it's centered at 0, but we'd like to test claims about sigma. And the goal here is to find a uniformly most powerful test of size alpha, where the null hypothesis is that sigma is equal to some number versus sigma is greater than that number. So we have an upper-tailed test, and if we can show that the data are from a one-parameter exponential family, one parameter because we've fixed our mean and so we only have sigma as our parameter, then we can talk about rejecting the null in terms of the d of x that we come up with. And so it turns out, you may have had this for a homework question, I can't remember, but you can relatively easily factor the joint distribution of the data in the following way. So 2 times pi times sigma raised to the negative n over 2 times e raised to the negative 1 over 2 sigma squared times the sum of the xi's squared. Here we have a c of sigma, and here we have our d of x. And so based on the result from the last slide, we can verify that this is an increasing function of sigma, and so that allows us to say reject the null hypothesis if d of x is greater than or equal to k, where k is such that the probability that d of x is greater than or equal to k under the null hypothesis is equal to alpha. Well, that's equivalent to the probability that the sum of the squares of the xi's is greater than or equal to k under the null being equal to alpha. And another way to write this, if we wanted it in terms of a distribution that we know, is to say, well, the sum of the squares of the data over sigma squared is greater than or equal to k over sigma squared under the null. And the reason why we did this is because now we have things in terms of the chi-squared distribution. So this quantity here is now chi-squared with n degrees of freedom, and we could think about this new term here as being a k1. And so we would just be finding a specific value, this k1, such that basically we would want to reject a chi-squared random variable if it's greater than or equal to the value that makes the probability of landing in that region alpha.